All right, we are finishing up Mod 12 with a look at some data here in StatCrunch. So let's go ahead into our StatCrunch spreadsheet that I have on the right, load the shared data set, roller coaster drops and durations, run that linear regression analysis, and see what we get. Okay, let's get our data set. I think if we just search for roller coaster, that will give us what we need. Scroll down, and here we go. Roller coaster drops and durations. So to run our regression analysis, we're picking stat, regression, and then simple linear. Let me get that to fit in your screen here. All right. So the paper says we're exploring the relationship between initial drop and duration. So we're going to use the initial drop measured in feet as our x variable. That's our explanatory variable. And then our y, our response variable, is the duration of that ride. We're not going to worry about any of these things in here. There is more advanced analysis that can be done, but that would not be in an intro course like this. That would be addressed in later courses. So let's move down and see what else we have. If you'd like to make a prediction of a y value from your line, you can go ahead and put in your x value here, and it will give you that prediction. This level of 0.95 is something that we will talk about in modules much later on. The graph is already set up to give us that fitted line plot, so that's good. Save. If you'd like to go ahead and take a look at your residuals, you can click there to have your residuals saved and click compute. And here we go. Excuse me. So for part A here, we've been asked to record the linear regression equation rounding to 3 decimal places. So everybody should pause, make sure they can find that, record their equation. Also take note of that footnote I have here. There is a page in OLI that's going to walk you through finding this regression equation from summary statistics and working that by hand. You would never ever need to do that for my class. We're always going to let our StatCrunch technology find this equation for us. Okay. Actually, take a pause here. Do both A, B, and C if you can do C, and then come back. Okay, let's take a look. So our regression equation is coming from here. I rounded each of the values off to 3 decimal places. And then for B, what can you say about the sum of squared errors or residuals for any other linear equation used to describe this relationship? Well, what you can say is that you would need to get a value larger than 3832.523, which is the sum of squared errors for this regression line. And remember, that came from right here. Sum of squared errors, the number right here, is what gives that to us. Okay. Part C. So we are interpreting the y-intercept of the regression equation. So remember that for any line, the y-intercept is the point at which that line crosses the y-axis. And anywhere on that y-axis, our x-coordinate is 0. So the y-intercept is the ordered pair for which the x-coordinate is 0, and when we put in an initial drop of 0, 9.061 is the value for the duration. So this ordered pair is our y-intercept. But what does this represent in the scope of our data? Well, remember, our x-coordinate is the initial drop measured in feet, and our y variable is the duration of our ride measured in seconds. So to literally translate this ordered pair, we are told that for an initial drop of 0 feet, the predicted duration of the ride is 9.061 seconds, which of course makes absolutely no sense at all. Very often when we are attempting to interpret a y-intercept in the scope of data, our interpretation just doesn't make any sense at all because we don't have any data at 0, and very often 0 just means nothing in the scope of our data. All right, let's go ahead and interpret the slope of our regression equation. So remember that the slope is the number that is multiplied to our explanatory variable to our x. So that is 0.877. And thinking back to algebra, somewhere in your past, you may remember the expression rise over run related to slope. And we're going to apply that here. But to think of this decimal number as a fraction, we will first need to make it a fraction. So to do that, we are going to put it over 1. Any number divided by itself is still that number. So we haven't changed it by rewriting it as this fraction over 1. Well, now we need to think about what is a change in rise in the scope of our data. Let's go ahead and look at that fitted line plot. So any vertical change here is a change in the duration of this ride. So the rise of our slope represents a change in that duration. And that is measured in seconds. What does the run in this data represent? Well, as we run across, our horizontal movement represents a change in the initial drop of that roller coaster. So to interpret our slope, we begin with the bottom of this fraction and talk about the change that would be predicted in the top. That's because the bottom, the run, is our explanatory variable, and the top of the fraction, the rise, is our response variable. So we're talking about how a change in our explanatory variable will be associated with a change in our response variable. And we're always going to be cautious to not use any words that imply causation unless this is data that has been collected during an experiment, which I doubt this data is. The one other thing we need to worry about here, though, is our units. So taking a look at the units we have right now, we're talking about a change in initial drop of just 1 foot and a change in the duration of the ride of less than 1 second. And if we kind of apply that to this graph we have over here, trying to move a horizontal distance of 1 foot really doesn't relate to the scope of our data. Trying to move up a distance of less than 1 second really doesn't apply to the scope of our data. So I think before we give our interpretation, a change in units will be needed. So to change our units, or to change our values, really, I'm not changing from seconds and feet, but I am changing my values in this fraction. I'm going to move my decimal point the same number of places in both the top and bottom of this fraction. So if I decide to move it just one place to the right, that gives me a change of 8.7 seconds in the duration of the ride. And to move my decimal point one place on the bottom, I need to add that 0, which gives me a change in 10 feet of initial drop. And that is much more realistic movement around this graph. I think if you had also decided to move your decimal point 2 places to talk about a change in duration of 87 seconds and a change in initial drop of 100 feet, that would work as well, but I'm just going to go with this, moving it 1 decimal place. All right, this is the interpretation that I came up with. An increase in the initial drop of 10 feet is associated with an increase of 8.77 seconds in the duration of the ride. And you do want to include which way this change is happening. This is a positive association, so it's an increase in an explanatory variable that leads to an increase in that response variable. All right, the next thing we're going to do is predict the duration of a roller coaster with an initial drop of 173 feet. The first thing you always need to do when you're asked to make a prediction is think about whether or not you should. And in order to be able to say you should, 2 things need to happen. One is that you need to have concluded that you have association between your 2 variables that is described by your regression equation. And that was our conclusion here. Taking a look at our scatter plot and our correlation coefficient, we decided that there was evidence of a linear relationship between these 2 variables. So it is reasonable to then use this equation to make a prediction. But the second thing that must be true is that the x value that we're given must be within the scope of our data. An initial drop of 173 feet right about here is within the scope of this data. So we can go ahead and make this prediction. Guesstimate from the line, it looks like maybe about 160, 170, something like that. But to get our exact value, we will take the x value of 173 and put that into our regression equation. Everybody take a moment to do that and see that we all get the same value. Okay, using our equation, I came up with 160.783 seconds. All right, our last question. Did a little research. The Steel Dragon 2000, located at Nagashima Spa Land Amusement Park in Mie Prefecture, Japan, has an initial drop of 307 feet. Should we use our data analysis to predict the duration of this ride? Well, hopefully, immediately you think, no, we should not. An initial drop of 307 feet is outside the scope of data that we have collected. The largest initial drop that we have data for is 261 feet, well short of 307. If we collect data out there, maybe the data takes a steep turn upward, possibly it continues in this linear pattern, or maybe it goes back down because that drop is so high, it makes that ride just so quick. There's no way for us to know what happens to the data outside of what we had collected. So we should never make any predictions out there. If we did, it would be called extrapolation, and extrapolation is almost always bad. This ends Mod 12. As always, if you have any questions, please reach out and let me help.